Please take your seats and be prepared. Pay attention. I am waiting for a signal from the director in the back, which you won't hear, but I will hear it. So thank you all for braving the weather. Come here about the opposite kind of weather. Well, not entirely, since cryovolcanism is pretty cold. I now call to order the lecture portion of the Society's 2,526th meeting in what is now the 154th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW Science, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry to as broad an audience as possible. Welcome to our members, guests, and friends to the lecture portion of today's PSW meeting and to the lecture by Rosalie Lopez on volcanism and cryovolcanism throughout the solar system. To start with, let's thank our sponsors. The 25-26 full-year sponsor, PSW Mike Helton and Helton Associates, LLC. Thank you, Mike. And 2025-2026 full-year sponsor, PSW member Joel Schulman and the Schulman Family Foundation, including the member here. The Society needs your support. We have expenses. Every lecture costs about $3,000 to $4,000, believe it or not. So if you can give, please do. If you've already given some, but you can give more, please do. And now is a particularly auspicious time to make a donation because PSW is the beneficiary of a very generous matching grant. Every dollar you give now through January 31st will be matched 2 for 1, up to the first $5,000 of donations. Because it runs both December and January, you can pick your tax year. So please give, and give generously to the extent that you can, and help us continue to give these lectures. I'm pleased to announce the following new members. Nan Zhu, professor of bioengineering at University of Maryland, interested in neuroscience, brain dynamics, computational neuroimaging, data analytics, and machine learning. Who learned at PSW, he says, independently. Marcos Kashioris, a physician scientist with Innova, interested in medicine, biostatistics, AI, and end-of-life studies, who learned at PSW from the internet, looking for organizations that, I quote, are free of political polarization in any way, where it is possible to have apolitical discussions across disciplines, close quote. Hear, hear. Glenn Merberg, founder and executive at Quadrant, interested in general engineering, novel medical science, machine learning, and AI, who learned at PSW from PSW Joel Bowman and Michael Adiamarco. Thank you, Joel and Michael. I think Joel's in the audience somewhere. Iago Pinal Fernandez, a staff clinician with NIH interested in medicine, autoimmunity, and computer science, who earned a PSW from Friends. I think he is in the audience, so let's welcome him. Nancy Matthews, a nurse practitioner retired from the Henry Jackson Foundation, particularly interested in autoimmunity and autoimmune diseases, who earned a PSW from PSW member and recording secretary Scott Matthews. Thank you, Scott. Zofia Kowalska, a student in the MS program in biotechnology at Georgetown University, interested in chemistry, life science, and biotechnology, who earned a PSW, and I quote, by asking Professor Milstein, that would be me, about the pin he was wearing at one of his lectures, which would be the 2,500th meeting commemorative medallion. And if you're curious about what that is, Jared at camera number 1 is wearing it, and you can see it. It's really a lovely pin. I wear it all the time because it's really very nice looking. And Michael Fitzgerald, an independent technologist interested in computer science and engineering who learned a PSW from PSW member Charles Huttner. And finally, Rosalie Lopez, tonight's speaker, who learned a PSW from PSW speaker and member Charles Norton, who unfortunately can't be here tonight, and from the invitation to speak here tonight, and whose interest will be clear, at least in part, from tonight's lecture. Please join me in welcoming them all to membership. All members are entitled to a signed copy of Compendium Volume 17 of the Bulletin of the PSW. And if you are a new member and you haven't received yours, please come see me after the meeting. All members are invited to the pre-lecture receptions and dinners with the speakers for camaraderie and interesting discussion, which I think we enjoyed tonight. And we had the treat tonight also of seeing some as yet unpublished and new, fresh off the telescope results brought to dinner by one of our members. Is that inaccurate? And that's one of the things that does happen here, which is in keeping with the founding of the Society as an analog in America of the Royal Society for the presentation of new scientific results to be discussed by scientists. If you're interested in membership, you can access a membership application on the PSW website very easily by clicking the blue Join button, all caps Join, on the home page at the upper right-hand corner. And if you're here in the Powell Auditorium, you can access the application using the QR code on the business cards that you'll find on the cocktail tables at the back of the room. Everyone with a genuine interest in science is welcome to apply for membership and to join. And with that, Recording Secretary Scott Matthews will now present the minutes of the 2,525th meeting and the lecture by Jeffrey Alexander on determining the true value of federally funded research, subtitled, Why We Should Continue to Support Basic Research.
Thank you, Larry. Good evening. On November 21st, 2025, members of the Society and guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2,525th meeting of the Society to order at 8:02 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, announcing new members, and inviting guests to join the Society. Scott Matthews then read the minutes of the previous meeting, which included the lecture by John Sunderland titled Medical Imaging with Antimatter, High-Resolution Positron Emission Tomography. The minutes were approved pending a minor correction. President Milstein then introduced the speaker for the evening, Jeffrey Alexander of RTI International. His lecture was titled The Real Returns on Public Research Investments. The speaker began by saying that when it comes to publicly funded research, he prefers the term value of investment over the term return on investment, or ROI. He indicated that ROI was a financial term and that value was, quote, more all-encompassing. Alexander presented data from the National Science Foundation, which estimated that the total U.S. spending on R&D in 2022 was about $930 billion, with $172 billion being spent by the federal government, as compared to approximately $709 billion spent by business. He said that of the $137 billion spent on basic research in 2022, the federal government funded approximately $56 billion. The speaker then posed the question, quote, what are we getting for the $172 billion we spent in 2022, end quote. He went on to describe possible ways to quantify R&D performance. The first was to express national spending on R&D as a share of gross domestic product, or research intensivity. He said that this method of measuring R&D performance was based on a linear model. The value of the output is proportional to the input. He indicated that research doesn't work that way, and he labeled this as, quote, the fallacy of causality. Alexander gave a specific example of the difficulty of measuring the ROI of research grants by discussing the $4.5 million grant awarded to 2 Stanford University professors, which enabled the development of the PageRank algorithm and ultimately the creation of Google. In 2005, the year of Google's IPO, Stanford sold its Google stock for $336 million. In 2020, Google's market capitalization exceeded $1 trillion. Using the former number, the ROI is approximately 7,500%, while using the latter number, the ROI exceeds 2.2 million%. The speaker referred to this as the fallacy of attribution, assuming that all of Google's market value is attributable to the PageRank algorithm and therefore to the $4.5 million NSF grant. The speaker then discussed evaluating research ROI using input-output models. He gave the example of the NIH awarding approximately $37 billion in 2024, which led to, quote, direct, indirect, and induced follow-on spending. He claimed that this investment supported more than 400,000 jobs and generated more than $94 billion in economic activity. He presented what he called the fallacy of uniformity, the assumption that every dollar spent on research produces the same impact regardless of the type. The speaker then discussed ways to estimate and quantify the results at various phases of development: publications for basic research, patents for invention and initial design, prototypes for development and scale-up, and products for production. He discussed the complex feedback mechanisms at each of these stages of development. He described how the sources of investment change with each phase of development. Government agencies like NSF and NIH in early basic research phases, angel investors and government agencies like DARPA during the design phase, and corporations and mission-based government agencies in the prototype and production phases. He said that the complexity of the system makes it difficult to ascribe any particular result or achievement to a specific investment. The speaker noted that in research, failure has value, and that it is very difficult to quantify the ROI of failure. At this point, Alexander stated his central thesis, quote, attempting to calculate the financial return on investments from federally funded research is a misleading, misguided, and incomplete assessment of the actual value generated by that research, end quote. He provided specific arguments and specific examples to support this thesis. He then described his opinion of a better way to show the impact of federal R&D spending. This included ways to characterize outcomes, communicate benefits, and quantify results. He described specific quantitative and qualitative indicators, noting that these indicators are proxies for the actual value produced. He gave an example from the technology transfer process at NIH, using patents, licensing, and royalties as quantitative indicators, tracing the impact of the initial investment on outcomes, including follow-on R&D, new products or services, job creation, and public health benefits. The speaker ended his talk by saying that any metric for quantifying the returns from federal R&D spending will always have shortcomings, but that focusing on purely financial analysis is misleading, misguided, and incomplete. The lecture was followed by a question and answer session. A guest asked Alexander if he believed that the private sector has more of a responsibility to invest in basic research by virtue of the fact that they capture the majority of the economic returns. Alexander responded that large corporations had centralized research labs in the 50s and 60s, but that they have largely disinvested in basic research for economic reasons. He mentioned that there has been a recent upsurge in R&D spending in the private sector, but this was almost all attributable to 3 or 4 companies. President Milstein asked the speaker if it was the case that a particular invention or therapy would not have made it to market without significant private investment, particularly with respect to clinical trials. Alexander responded that this was the case, and that the attributional benefits should be shared amongst all the investors. He indicated that for most vaccines and medical therapies, the private sector invested more than the federal government. A member asked about, quote, soft power. Does the federal funding of R&D enhance the reputation or brand of the United States? Alexander responded that federal investment in R&D helps to demonstrate our goodwill and that, quote, science diplomacy is a real thing. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 17 of the PSW Bulletin. He then announced speakers of upcoming lectures and made a number of housekeeping announcements. He adjourned the 2,525th meeting of the Society at 9:59 p.m. Eastern Time. Temperature in Washington, D.C., 11.1 degrees Celsius. Weather, cloudy. Audience in the Powell Auditorium, 73. Viewers on the live stream, 21, for a total of 94 viewers. Views of the video in the first 2 weeks, 145. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Scott. Are there any comments, additions, corrections to the minutes? Hearing none, I will entertain a motion by a member to accept the minutes as read. Thank you, Bob. I have a second. Thank you. All members in favor of accepting the minutes as read? All members opposed? The minutes are accepted unanimously, I think, as read, and will be posted to the website in due course, subject to any pressing comments that come in electronically. And it's now our pleasure to turn to tonight's lecture by Rosalie Lopez. Rosalie is a senior research scientist at NASA JPL, adjunct professor of astronomy at Cornell University, editor-in-chief of Icarus, president of the Planetary Sciences section of the American Geophysical Union, and principal investigator on NASA's project on habitability of hydrocarbon worlds, Titan and beyond. Her research focuses on planetary and terrestrial geology and volcanology. She served on the Galileo mission team and was responsible for observations of Jupiter's moon Io and its extraordinary volcanic activity, during which she discovered 71 active volcanoes on Io, the largest number known anywhere in the solar system. In fact, the largest number known anywhere at the moment. The discoveries earned her a spot in the Guinness Book of World Records. She also contributed to the Cassini mission to Saturn and its moons, and she currently is leading a team studying Cassini data on the geology and potential habitability of Titan. She's an author on more than 135 scientific publications and 8 books. She's lectured about her work on every continent, including Antarctica. and she's appeared in more than 20 television documentaries. Among many honors and awards, she's a fellow of the AAAS, GSA, and the AGU, an elected member of the International Academy of Astronautics, a recipient of 2 national NASA Exceptional Public Service Medals. She's also the recipient of the Adler Planetarium's Women in Science Award, the NSF Antarctica Service Medal, the Explorers Club Lowell Thomas Medal, the Wings World Quest Women of Discovery Air and Space Award, and the American Astronomical Society's Carl Sagan Medal. All of which I'm telling you so we can get to the last part. Last but not least, she is enshrined in the heavens above. Asteroid 22454 is named Rosalie Lopez in her honor. She earned a BSc in astronomy and a PhD in planetary science at University College London. All questions will be fielded after the lecture during the Q&A session. And with that, Rosalie, the stage is yours.
Thank you. Thank you so much. It's indeed an honor to be here and a pleasure. This is a wonderful club, and looks like a really, really interesting society. And as you could see from the biography, I lived in London, in England for many years, and I used to go to lectures at the Royal Society, so it was good to hear that this is the equivalent of the Royal Society in the US. So I'm going to talk tonight about volcanism in the solar system, and starting a bit with volcanism on Earth. My PhD advisor told me that you can't understand volcanoes on other planets if you don't understand them on the Earth. So, and right in my first year, he dragged me along to Mount Etna in Sicily as part of his team of expendable students. So this picture was taken at Yazur volcano in Vanuatu, in an island called Tana. It looks very fierce, but in fact, this is one of the easiest volcanoes in the world to visit. And I can tell you more about that later. Although it was a very unusual picture because I don't normally have my back to an erupting volcano. But someone I was with said, I seen all these books, and I never seen a picture of you with a volcano behind you. It's like, yes, there's a reason for that. And anyway, volcanoes in the solar system, so that's real pictures of the planets, but of course not to scale in terms of distance. And so volcanism is actually a very common process in the solar system. We see evidence of volcanoes, Mercury, Venus, of course, Earth, Moon, Mars, Vesta, Ceres, Io, several icy moons, and likely some exoplanets. The ones that I underlined are the ones where we have evidence of active or recently active volcanism. So the picture is a volcano in Hawaii, in fact, Kilauea, which is erupting at the moment. I should be there, but with luck, when I go there in February, it will still be going. And we call this is like 30 feet high, that lava fountain. It's called a lava fountain, or a more popular name is a fire fountain, and it's one of the most beautiful things that you can see. So the surface of every solid planet you see, the Earth, the Moon, Venus, Mars, whatever, it represents an interplay of the 4 basic geologic processes, and those are volcanism, tectonism, impact cratering, and erosion. So on Earth, we have a lot of erosion. We have plate tectonics, so old crust gets destroyed. We have erosion by water, rain, wind. On the moon, you don't have erosion, except a tiny bit by micrometeorites. So old surfaces are much better preserved. And on Earth, impact craters are relatively rare. And that's because impact craters were mostly formed in ancient times, closer to the formation of the solar system. And on Earth, most of that record has been erased. And you see here a meteor crater in Arizona. That's the best preserved impact crater that we have. Where are the volcanoes on Earth? Well, they're along the plate boundaries. And this picture represents the plate boundaries in blue, earthquake zones in yellow, and active volcanoes in red. And as you can see, California, lots of earthquakes along a plate boundary. You don't have here this here in DC. So there are different types of volcanic activity, and this is to so that we can understand the ones on the planets. So on Earth, they've been given names, such as Hawaiian and Icelandic, Strombolian, Pelean, Vulcanian, Plinian, and Ultraplinian. And in fact, that classification, although it's not terribly scientific in many ways, but it's very useful. Because, when we talk about a Hawaiian eruption, we have an idea of what it is and what it isn't. And that classification was actually started by Mercalli of the earthquake scale fame. So they are mostly, like Hawaiian, Icelandic, representative of the locations that have them. Plinian and Ultraplinian is just a big Plinian eruption. Those are extremely nasty, very violent eruptions. And Plinian was named after a man, Pliny the Elder. He actually witnessed the beginning of the Vesuvius eruption in 79 AD. He was a general in the Roman the Navy, actually. He was like an admiral of the Navy. And he went to try to rescue people, and he died in that process. His nephew, Pliny the Younger, was able to observe what was going on, and he wrote a description to a Roman historian called Tacitus. And that is the first scientific description of a volcanic eruption that we have. So that's why that type of eruption is named after him. So these different types of eruptions build different landforms. So we have here, trying to get, Icelandic eruptions. They tend to form long fissures, lots of lava come out like in a sea of lava. Shield volcanoes in Hawaii, they look like a warrior's shield. The name came from Iceland as well. And they are formed by the accumulation of many lava flows. Then you start getting the explosive eruptions, Strombolian, Vulcanian, Pelean, Plinian. And they build cones. So I remember being in Hawaii, overlooking Mauna Loa volcano, which is like this low shield. And a tourist nearby said, that doesn't look like a volcano. Why? Because, people's idea of a volcano is these cones like Mount Fuji, but they aren't all like that. And what causes different types of volcanic eruptions? Mainly the composition of the lava. That is a type of rock. So the shape of the volcano, the type of eruption, gives you a clue of the material involved, and that's one of the things that's important for planetary volcanism studies, because even though we can't always, go there or get samples from the surface or tell the composition, but from the shapes of the volcanoes, from the type of eruption, we can tell something about the composition of the rock. So the basalts, the dark rock, like we have a lot in Hawaii, the basalts have low SiO2, silica dioxide content, which means that they don't form strong bonds, so the lavas are very fluid. Then when you get to andesite, dacite, and rhyolite, they have increasing SiO2, so these bonds are very strong. Now what happens when lava comes out of the ground, it has gases dissolved in it, the gases want to come out. If the lava is very fluid, the gases just whoosh out like in that fire fountain. If the lava is very viscous, then the pressure builds up and builds up until it explodes. So they form the andesites, dacites, rhyolites, form those explosive eruptions, which are the ones I don't like, because they're very dangerous. And, luckily for people who like to go to volcanoes, photograph them, the most beautiful eruptions are actually the least dangerous. Hawaiian and Icelandic eruptions are really beautiful. Here is lava going into the ocean down a cliff in Hawaii, and this is in Iceland, just along a fissure, and over here is Iceland as well, and here is a lava lake in Hawaii. So they're very beautiful. Strombolian eruptions, named after Stromboli in the Aeolian Islands, they form mild to moderate explosions and form cones. So, here is a group I was with who were overlooking the crater. And, that is not all that dangerous, that type of eruption, but you really have to watch those fragments that come out, which we call bombs. They don't explode, but they're called bombs. And that's why I didn't want to turn my back on that volcano to get a picture taken. But if you're careful, you know what you're doing, you're okay with those. And this is a movie from Yazur in Vanuatu, so that you can see there is like these gases are coming out, but in small explosions. And as I said, this is a really easy volcano to visit. Mount Etna can be very tricky. And most of the time it erupts lava flows, but here this picture was taken by a colleague of mine when they were, just looking at these explosions getting, bigger and bigger, and eventually they did what you should never do with a volcano, which is turn your back on it and run. but in the end they had to do it. So that's very ash rich eruption. And then Peleans after Mont Pelée in Martinique. There was an eruption on that island in 1902, which killed about 30,000 people. It was really bad. And they didn't know that Mont Pelée was a volcano, and it hadn't erupted before. And there was this beautiful city of Saint-Pierre, which now has been rebuilt. And a pyroclastic flow, which is, this is one in Montserrat. It's the nastiest thing that a volcano can put out. This cloud of ash and hot gases, that's what killed people in Pompeii and Herculaneum. And at the top there is Mont Pelée as it looks like today. Has not erupted since. And the Plinian and Ultraplinian, we had an example here, Mount St. Helens in the US in 1980. That was a Plinian eruption. Again, killed a number of people, but, lucky only about, if I remember correctly, like 30 and a few. Now let's go to the moon then. The moon, no atmosphere, no erosion, no plate tectonics. So we're looking at very ancient surfaces. And when you look at the dark areas on the moon, those are the remains of floods of lava. So they would be like a more extreme example of Icelandic eruption. They would be seas of lava, similar to what existed on the Earth 3-4 billion years ago. And most of these lavas on the moon were in place up to about 3.5 billion years ago. So they're really ancient surfaces. And the bright surface are all dominated by impact craters. So you have the crater Tycho at the border, at the south, near the South Polar region here. And the moon then has this seas of lava. And in this picture over here, you can actually see some lava flows. These are Mare Imbrium. That's an Apollo 15 image. You see some lava channels. Here is Hadley Rill, is where Apollo 13 landed near here. And a few cones. Those are some small cones. This image is about 80 kilometers across. But, very few and pretty small. There are some very mysterious regions on the moon called irregular Mare patches. And scientists are still debating on what these are. It's being proposed that they were lava flows with a lot of bubbles. But there are other people that say no. Actually, they're too young to have really been formed by volcanism. On the other hand, the Chinese rover found that volcanism on the moon ended in tens of millions of years ago, which is relatively young in geologic terms. So this is an area really to be investigated. Sometimes we think that we know everything about the moon, but far from it. Future moon missions will, hopefully be able to shed more light in that. Mercury, Mercury was strange. When I was doing my PhD, we didn't know if Mercury had volcanism or not, because it had smooth areas similar to the moon. But there were some researchers who thought that those were impact melt, not volcanism. And it was really only with the Messenger mission to Mercury, done by APL near here, that we actually figured out that yes, a lot of volcanism happened on Mercury. And you see here one of the telltale signs is this crater, because volcanic craters are irregular because they're formed by collapse. Impact craters are very circular because they are formed essentially by shock waves. When the meteorite comes along, impacts, excavates that material. So that was actually came out of work done on Meteor Crater by Eugene Shoemaker, that he found that impact craters were similar to craters formed by nuclear explosions, for example. So they are excavated by shock waves, and they're very circular unless it's a really glancing impact. But, a crater like this, with, just this irregular shape, and other there was other evidence from composition and so on, showed that Mercury had a lot of volcanism in its past. Venus, I have to say the colors are artificial. Venus had a radar mission, and with radar data you don't get color. But they colorized this image, and it's is a computer-generated image here from the radar data, showing it 3D perspective, and the colors came from like the Venera colors that the Soviet missions had seen, although they were not quite as bright. So Venus has shield volcanoes. There's a shield volcano, lava flows here in the foreground, slightly different radar signatures, so you can see the lava flow. It's got a number of calderas, and that's one of them. And it's got some funny features that got nicknamed pancake domes because they look like pancakes. And this is more obvious in this. This is a painting done by Michael Carroll, who is a space artist, also a writer. But this is how we imagine these pancake domes on Venus will look like. And why are they like that? Because we have domes on Earth too. If you have lava that is very viscous, but has very little gas dissolved in it, then it's just going to ooze out. Some people call it toothpaste lava because, kind of oozes out like that. So that's Michael's view of the pancake domes. But there was a lot of suspicion that from various lines of evidence that Venus might still have or have recently had active volcanism, but no one could quite prove it until some colleagues quite recently did some work on the Magellan data. Magellan lasted about 2-3 years, I want to say, the mission. So these two images here from near this shield volcano called Mat Mons, these two images actually show differences if you look at them closely, and this means that actually, new lava actually came in months between these two images. And what's interesting is that the main guy who did this analysis with a person at JPL, because you really need a lot of radar expertise to analyze these images. They were taken from different angles, and I worked with radar on Cassini, and there are lots of things that can fool you. So after a lot of work, they convinced themselves that, this was a new flow. Sorry, I'm turning my back. And this is a vent that was unchanged, and this is a vent that was expanded. And they actually told me that they couldn't have done that back in the Magellan days in 1990 because there wasn't enough computing power and capability to actually do the analysis. So that made Venus even more interesting than we thought it was. Mars has the largest volcanoes in the solar system. This one here is called Olympus Mons. That's the first volcano I studied because why not start with the biggest? So, and this is a topographic image. Mars has this kind of dichotomy of some parts are higher. You can see here the scale, and some are lower. But Mars has gigantic volcanoes. So, like Olympus Mons is 600 kilometers across and 26 kilometers high. And actually, if you think about the ratio in your head, it's very gentle slopes. People joke that it would be fun to ski down Olympus Mons. And there's some data from Global Surveyor, what we call the three Taurus, giant volcanoes, and Olympus Mons. And my first project was to figure out what this material was around Olympus Mons. It's shown here in green. It's a very corrugated material, which we concluded were landslides, giant landslides that left behind this scarp around the volcano. It's still, I don't know that's totally accepted, but it's still like a good explanation for it. And this Michael Carroll painted a view of a volcanic eruption triggering a flash flood. And, my idea when I wrote this first paper with my advisor was that Mars has permafrost on the ground, and that if a volcanic activity was renewed, it could have melted the permafrost, and that could have lubricated the landslides. And of course, we have had loads and loads of Mars missions, but that could be another talk. And so I'm just going to show, something recent here, that the Curiosity rover actually found sulfur. This, field of, pointed out here, of bright sulfur. And if you ever visited a volcano, you know that you find a lot of sulfur on volcanoes. So that was an exciting result from the Curiosity rover. And actually, Sirius has a mountain here, is a 2-time vertical exaggeration that we think is a volcano as well, but this is another type of volcano. It's a suspected cryovolcano. And we'll talk a bit more about that later, but I was just like going in solar system order. And so cryovolcanism happens when the material that erupts is not molten rock, but is actually water with some, other components, but mostly water. So this is a suspected cryovolcano from Ceres, which is an asteroid that has a layer of liquid water under its crust. So that was a very exciting discovery by the Dawn mission. But my favorite body, well, actually I have two, is Io and Titan, but Io is the most volcanically active body in the solar system. It's about the size of the Earth's moon, so we expected this would have cooled long ago and become dead like the moon. And it was a surprise when Voyager, this is an image from the Voyager spacecraft in 1979, found active volcanism. But it, in fact, had been predicted by probably the best timed paper ever. Just a couple of weeks before the Voyager flyby, these scientists who were astrodynamicists, they looked at the orbit of Io around Jupiter, and they realized that because of the other moons out there, there would be this push-pull, gravitational push-pull that would raise tides, and the friction from those tides could keep the interior molten. And they even said that widespread and recurrent volcanism might occur. And that was 2 weeks before the flyby. I mean, how good is that? I don't think anyone has topped that yet. But I worked with the near-infrared mapping spectrometer on Galileo, and that's an image at 4.7 microns taken towards the end of the mission in 2001. And and I used to go through all these Io images, and we had to project them very carefully, and there was a lot of pointing corrections to be done on Galileo, on the Galileo data. And then I had to look at this pixel by pixel, compare with the nearby pixels, because some of the volcanoes are obvious. This actually saturated the instrument in white. But, others were much more subtle. And that's why I ended up finding 71 volcanoes that people didn't know, because Voyager only found about a dozen. And now with the Juno data, we found a lot more, and there are over 300 volcanoes known. But the thing about the Guinness Book, it started out as a joke that my colleagues on the team, I would send emails like, oh, I found another 2 or 3 active volcanoes. And it's not the most important scientific result, let's put it this way. But, it was cool. And they started joking with me that you should be in the Guinness Book of World Records. And, a few years, actually, a couple of years after the mission ended, I got a postdoc who came from England, and he heard that joke, and he said, you know what? I have a friend who works for the Guinness Book of World Records. Not only that, this friend was at his university, had started a PhD on IO, but then given it up and gone to work for Guinness. And, and he had to tell his friend about that. So in the 2000, and actually the friend asked for my papers and names of colleagues and, did all this investigation. But, I didn't think I would ever be in the Guinness Book of World Records. But in 2006 book, there is a little note. It's not a category. Anyway, it was a lot of fun to find these volcanoes. And this is the discovery I was telling you about. This Pill, Casson, and Reynolds in 1979 in Science, 2 weeks before the encounter. And that's what they said. One might speculate that widespread and recurrent surface volcanism would occur. And, so here's Jupiter, here's Io, the orbits of Europa, Ganymede, and Callisto. And these orbits are in resonance, which means that for every, let's say, 2 orbits that Europa does, Io does 1. And if the other moons weren't there, if there wasn't this resonance, Io would have its tidal bulge facing Jupiter. There wouldn't be any volcanism at all. But because these other moons are actually pulling that bulge, and then Jupiter pulls it to the other side, that creates a lot of friction, and it keeps the interior molten. And so that was an amazing discovery, because it also led us to think of, tidal energy as something really important in the solar system. And this is how Voyager found the active volcanism. It was this image, which was not taken for science purposes. It was taken for navigation. That's kind of a crummy image. And a young engineer called Linda Morabito noticed that there were 2 very unusual things. The one on the limb, she even thought might be another moon that was undiscovered. And this planetary geologist had already noticed that Io's surface was very young. There were no impact craters at all. When they saw that, and later they saw a plume from, there was no doubt. And then the infrared instrument detected SO2 in this plume, and there was no doubt at all that volcanism was happening. And for a while, there was a debate about whether it was a sulfur volcanism, because they had detected a lot of sulfur. The colors of the surface are sulfur. But even before Galileo, from Earth-based observations, it was found that the temperatures of some of the volcanoes, some of the lavas, were too hot to be sulfur. There are different volcanic styles on Io, and let's see how I'm doing for time. I'm going to go briefly through them. So this is a beautiful picture of Io taken by Galileo. And you see here a big red region about 1,000 kilometers across. And that's a plume deposit. So that's sulfur, likely S4. That it's red. And then another a volcano on top of that sulfur deposit that, I'm going to show a picture in a bit. So there are different types, just like on Earth we have different types of volcanism, there are different types on Io. And, so one of them is what we call flow-dominated or Promethean after this volcano that's called Prometheus. So it has a caldera over here and a lava flow that's, around 100 kilometers long. This is data from Galileo, data from NIMS, which actually shows that, it's hot near the vent, gets again hot near the front, most likely what we call an insulated flow, and that's something that flows in a lava tube, like we have in Hawaii. The picture below is more recent, is from the Juno infrared instrument, which shows that the pattern has changed a little bit. But what was most incredible about this particular volcano was that between Voyager, which is this image, and Galileo, which is this image, if you actually compare with what's nearby and kind of measure it, you realize that the plume that used to be here, and in 79, and then in 1996 was here, had actually moved about 90 kilometers to the west. And we all said, volcanoes don't move, not like that. So what's going on here? And a colleague of ours, very, very brilliant, called Sue Kiefer, all kinds of awards. We brought her in to help out on that, and she figured out that what was happening was that the flow was melting through this substrate on Io, that's SO2 frost. And then the SO2 frost was exploding through the flow. And that was what was creating the plume. And since then, we found other evidence on Io. It's not the volcano that moves. It's just the plume, because the flow is creating the plume. So as the flow moves, the plume also moves. And this has no counterpart on Earth that we have seen. This is very unusual. Another type is a very explosive eruption. So this was a little, nothing, little caldera on Io. In fact, it was one of my 71s. And then suddenly, in 1996, between April and September, we took these two images, and it's like, wow, this, what we presume to be ash, the gray area, it's about the size of Arizona. So it's really big. And it had a plume as well. But, these are very violent episodes that can be short-lived. But they can form much taller plumes than the Prometheus volcano. So this one was over 200 kilometers. This is an image from the New Horizons spacecraft on its way to Pluto that we were able to do some images of Io, and that's like 350 kilometers high, this plume from another volcano. And so plumes are fun. Galileo actually flew through a plume, but we didn't know it was there. We didn't know it was going to be there. And we survived. And the other type, my favorite type, are the lava lakes. So lava lakes are pretty rare on Earth. We have like half a dozen known. But on Io, they appear to be the most common type of activity. So this is a volcano called Loki, a a caldera that's about 200 kilometers across. This is some NIMS data, a temperature map, and this is at 2.3 microns. So I started seeing these hot edges, and then the imaging team took an image at night from another volcano and saw this hot edge as well. And hot edges are what you get on lava lakes on Earth, because what happens, lava is a very good insulator once it cools. So the lava lake forms a crust on top, but underneath it's still molten. And so this crust sloshes around against the walls, and it breaks. You can think of scum in a pond, and that's the effect it has. For Io, we started seeing, these hot edges, and we saw a few with Galileo, so I published this paper, and at first I wasn't sure, and the title of my paper was Lava Lakes on Io, ? And then, this is rare, but one of the reviewers said, there is no doubt, take that question mark off. So that was a very helpful reviewer. And this is another of the lava lakes, but just on one side. Some volcanoes on Io have cold islands in the middle, and we have not figured out what they are. And, in the visible images, everything that is hot is dark. So you see here, it's not only the edge of the caldera, but actually even around the island, looks like someone has drawn with a pencil. And is this crust breaking against the sides. And, around this time, Michael Caro, the space artist, was the first contact I had with him. He called me and he said, I want to paint a new volcano on Io for an article I'm doing, and what do you suggest? And I said, I think this crater is really interesting. There is some green material on the side that we think it's sulfur that's melting down from the walls, and the reds, there's reds and greens we think are molten sulfur. So he painted this view of the interior of Tupan, and we had lots of debate, brought in other people, to make sure that the angle of these jets was right. It's a lot of fun working with artists. And I like that so much that I bought the original, and it's in my office. But the Juno mission that's around Jupiter recently was able to capture some amazing data on Io. It has a really good camera. It didn't fly very close, but the images are really, the detail is really great. And also got a lot of infrared data. Now, Juno was not supposed to look at Io at all, but after it did its main mission, which was really to study Jupiter, it had this opportunity to do some satellite observations. And then I started collaborating with the teams, and that's another lovely image. You can see some very tall mountains at the bottom, and some of the volcanic calderas, and after the first of these flybys, the colleague I was collaborating with, and he's in Italy, he's the principal investigator for the infrared instrument, GIRAM. He wrote me an email and said, we see these hot rings, and what are they? And I said, I know exactly what they are. They are the lava lakes. But we saw the amazing thing. Here's Tupan, and here's another one, and and more of them, and the things that we saw so many. Io didn't just have a few lava lakes, but it appears that the most common type of volcanism are lava lakes, and hopefully, yes, it's playing. It's not very good resolution, but this is made from real images, but colorized and all that. So this is the Loki volcano with the lava lake in black, and the to study lava lakes on Earth, to be able to compare let's say, the infrared patterns and all that, it's not that easy because there aren't many lava lakes on Earth. And even before Juno, I and a couple of colleagues were already studying lava lakes. And then we decided to go to the ultimate lava lake, the best one. And the best one is in Ethiopia. It's called Ita Ali. It's very close to where this recent volcanic eruption happened that they said had not happened for thousands of years. That's another volcano, but very close to this one. And so that's actually me. And for people might know her. That's Serena Diniega from JPL. So we arranged this expedition, not NASA funded, because I just hate to think what our safety people would have thought of that. But, it was a nice vacation. And we went to this region that even people from Ethiopia have told me, you went there? Because it's very tribal and it's potentially very dangerous. But we were fine. And the lava lake, this is not my picture. There's a picture taken by another colleague, but it's just fantastic. And you can get right to the edge. And it's, as you can see here, that's my colleague Janie Radebo filmed that. And you can see here is the wall of the crater. So you can see here how the materials hitting the walls and becoming very, it's very mobile. It's like a sea, but it has this crust. So this was just amazing, and we took some infrared data as well. And this is, other than the gases, it's not particularly dangerous to, be there. Sometimes you had to kind of get back because it got pretty hot. And Ethiopia is a very hot place anyway. This is infrared data. And this is on a paper that we wrote. These temperatures are in Celsius, so you can see just that region I was showing the temperature data. And we went to another volcano in Vanuatu. This in Vanuatu archipelago I was telling you earlier in the first image of the talk about Tana Island, but Vanuatu also has, or used to have, doesn't have anymore, a lava lake in this island called Umbrium. So the caldera here is about 12 kilometers across, and inside there is a lava lake. So some of you might recognize, despite the masks, Ralph Lorenz and Zibi Turtle. The guy in the back is Bob Howell. Yes, and this is another one of my crazy ideas. And this expedition was actually thanks to a Brazilian film crew that wanted to film me on a volcano, and they suggested Ita Ali, but a couple of years before, some European professors had been killed there, not by the volcano, but by the locals. And I thought, no, in Vanuatu, I know the the residents are a lot more friendly. And so this lava lake was also fantastic. We're looking down on it. And some of you may have seen a video of some crazy Australian guy who actually, rappels down to the lava. He doesn't quite get to the lava lake. And the Brazilian film crew brought a guy, a couple of climbers to do the same. And in fact, with the TV angle, it looks like they're right there, but they weren't. It was a very risky thing to do because you see the walls are very friable, and I decided not to do this for kicks. But this is the lava lake, and it's very different from Ita Ali because this is really very turbulent. So it's not what we're seeing on Io because we're seeing those hot rings, which means that the lake can form a crust. But it's time that we went to cryovolcanoes a little bit. And here is a view taken by New Horizons as it departed Jupiter. And there is Io with its a big volcanic plume. And here is Europa. And, if you just look at this, it's like, I think Io is a lot more interesting. But actually, Europa has its, its very interesting aspects. Now, Europa is a place that had cryovolcanism. And this image is color enhanced from Galileo data. It has some regions that we call chaos terrains, that are very chaotic and jumbled fracture, has all these fractures in the crust. And that's where we think that material from the interior ocean has come up. Mm-hmm. And to help you understand, Michael Carroll did this artist view of two possible scenarios of Europa's interior, one having a thin crust of a few kilometers and the other a thicker crust. But we think Europa has volcanism on the ocean floor, and and the material comes up and even forms some plumes that have been detected by HWT, the Hubble Space Telescope. Although they don't seem to be constant like on Io, and there's still, some doubt about some of the detections. But our mission Europa Clipper is on its way. So here is one of those plume detections I was talking about. And Europa Clipper is really going to do a good job of studying Europa and finding out the thickness of the ice crust, the composition of the surface, is there organic material, and so on. There is a lot to learn about Europa, and it's one of the places that possibly life could have evolved. Why? Because you have heat, you have energy, you have water, and those are, we don't know what all the ingredients are, but those are some. And if Clipper finds organic material as well, then that's really going to be very interesting. But talking a little bit more about another place that has cryovolcanism, and that's the moon of Saturn called Enceladus. And it was known for some time that Saturn has a bunch of rings, but it has one very tenuous ring that's called the E ring. And Enceladus, the Enceladus orbit is right here, coinciding with this ring. So there was a suspicion that perhaps Enceladus could be causing this ring. And Cassini found very interesting, even back in 2005, first the magnetometer showed some suspicious signs that something was happening in the South Pole. We found these cracks in the ice crust that are known as tiger stripes. And then the infrared instrument found that the cracks were warmer than the rest of the surface. And the imaging team found jets coming from the surface. There are more than 30 jets in this image. So this material is coming from the interior. And here, Michael Carroll made a view of what would be like if you were standing there. Scientists, we often have difficulty thinking, what do you mean standing there? But it's quite a nice exercise. So There is a global ocean inside Enceladus and active jets in the South Polar region. And, and there are some things that make Enceladus really, really interesting. And some argue more interesting than Europa. First of all, Enceladus is spewing out this material that we actually know is coming directly from the ocean. Some of the things that Cassini detected, silica nanoparticles, it shows that the ocean is in contact with the core, and we think hydrothermal activity is happening at the core where it meets the ocean. So this is like hydrothermal vents on Earth, where you actually find a lot of life, and the fact that the plume activity begins in the core and is not just in the near surface, that's something that is a very interesting, raises a very interesting possibility for a habitable environment. And there were, salts detected as well, and this is a model of what the interior may be like. And Enceladus is just spewing out this material. So you could have a spacecraft there flying through a plume. We didn't have the right instruments to, sort of detect life. We detected a lot of promising signs, but it's certainly a destination that's high on everyone's list, as a place to go to. Titan is the other moon I study. It also has, a liquid ocean under its ice core. In recent times, this ocean may be more like pockets. There's a paper that came out recently. Titan in visible wavelengths, you can't see very much on the surface because it has a very dense atmosphere. So this is from Cassini. The long strips are radar, and the background is with the infrared instrument. So, again, if cryovolcanism is happening, the magma is coming up from the deep ocean. And the most promising sign we found was in a region here that this is radar data, so it's a little difficult to explain, but to understand. But you see here like a crater, and this is a topographic map, digital terrain map, and it shows two peaks that we think are the cryovolcanoes, and one of them. This crater is actually over 1 kilometer deep and is next to a pit that's over 1 kilometer high. And that really makes you think that this is a cryovolcano. And that's, it's slightly vertical exaggeration, but that's the volcano which got the name of Deux Mondes because, it was found around the time of the Lord of the Rings movies. And this is the pit. And there is a movie here that hopefully will play, yes. So this is false color, but it shows that the areas that we believe are cryovolcanic are actually different from the rest of the surface, and that data came from the VIMS instrument. So, there is, not everyone, thinks is a cryovolcano, and we certainly have not detected any thermal activity. So I think my colleague Connor, who is here, made a reference to the dog that didn't bark. I think that's from Sherlock Holmes. This is a topographic. Now we're changing the colors to topography. So, who knows in the future what we might find. And finally, Pluto from New Horizons. Actually, we found a couple of features. on the edge of that big Pluto heart that we think are possible cryovolcanoes. They have there's like a series of rings, and it's possibly the largest cryovolcano in the solar system. And the story may not necessarily end with Pluto, because there are exoplanets, such as this one is an artist concept, but where very high temperatures have been detected. So it's possible that volcanism may be happening there. And, a young man I have been working with, Apurva Oza, tracked the motion of a Sojourn cloud and found that around an exoplanet, and actually suggested that it's an exomoon like Io that's spewing out sulfur, and that and that's why you detect this sulfur cloud. So that's it. I'm sorry if I really took a lot of time. So thank you very much for all your attention.
Question time. So I have time for some questions. There's a procedure. There are two people with microphones, and if you raise your hand long enough, eventually a microphone will get to you. And I will call on you by the color of the windscreen on your microphone. When I do, please stand. Tell us your name, if you're a member or you're not, and ask a question. Please save the long commentaries for the social hour. Red microphone.
Thank you. My name is Mike Hilton. I'm a member. Thank you for a very good dissertation about the volcanoes in our solar system. My question is very technical and very deep, and probably you can only answer it.
Oh, dear.
The question is, how did you get interested in planetary physics as a little girl or young lady?
Okay. I grew up hearing about the Apollo program, and I wanted to be an astronaut, and then I realized, I was female, Brazilian, and with terrible eyesight until I had surgery. So I wasn't going to make it, and I just decided to study astronomy, and I love looking at the moon and stars, and I thought I'm going to help the astronauts, so that's what I wanted to do. So I was greatly inspired by a woman. I saw a photo of her in the newspaper in Brazil. Her name is Frances Northcutt, and she used to be work for TRW and was a contractor at Johnson Space Center during Apollo 13. And she calculated the trajectory to bring them back. She was a mathematician. And it took me many years to actually find her, because she left the space program and became an attorney. So it was.
No.
Yeah, I know. Yeah, I should have asked you.
What a
But we actually connected a few years ago, and it was great.
Did she become a patent attorney by any chance?
What?
Did she become a patent attorney by any chance?
No, criminal defense attorney.
Okay. Really?
Yeah.
Blue microphone.
I'm Bob Hershey. I'm a member. What looks promising for volcanoes in future missions?
Oh, there's a lot that looks promising. Well, we're sending Europa Clipper to Europa, and what I really want to know is, are there really plumes there? Are they just so faint that we can't often see them with space telescopes? Are they only erupting now and then? Where are they erupting from? So that's something I really want to know. And I'm now involved in the study of a concept for a spacecraft to actually fly through that Prometheus volcanic plume on Io, collect samples, and bring them back to Earth to be analyzed in the lab. That can tell us not just about composition of the lava, but being the first samples from the Otto solar system, could, analysis of like isotopes could tell us an incredible amount.
What's the timeline for that mission?
Actually,
30 years?
No, it doesn't take that long.
No.
It's. I even hope to still be around when at least when the mission gets there, But the timeline depends on the mission being picked and funding, and all those good
No,
things.
I mean, how long does it take to get there and come back?
It's like
15 years?
now it's less than that. It's like 9 years, I think. 9 or 10.
Red microphone?
Michael, remember, is Jupiter's Great Red Spot anything to do with volcanism?
Oh no. That's like a cyclone, an atmospheric phenomenon, and I have my colleague here, Heidi Hamill, who is an expert. So she should tell you about that. Jupiter has no solid surface, so long way down. It probably got metal core, but it's not a volcano in the way that we would define it.
Blue microphone, and then we'll go to the web, and then we'll get a red microphone. But blue microphone.
Kiprian Ivanov, member. Can cryovolcanoes exist in the proximity of magma volcanoes, and can an eruption of a magma volcano trigger eruptions from cryovolcanoes?
That's a really interesting question. We have not directly seen that, but there is actually a feature on Io, and Io has all these magma volcanoes, hot lavas and all that. But there is one place, one small crater that has a covering of SO2 frost or ice. And it's our analysis with the infrared instrument shows it's really pure SO2. It's like the purest we ever saw on Io. So we think that actually may be a case of cryovolcanism on Io. But it's a difficult thing to study and to say for sure. Yeah.
From the web?
We have a question from Michael Hacken, who is a member streaming from Maryland. Michael wants to know, do you have any thoughts on possible heat sources driving cryovolcanism and other geologic activity on Pluto?
Yes. It's the thinking is that it's tidal energy. So that's really what could cause cryovolcanism on a body of that size. I think we had a question there that the gentleman hasn't had a chance to ask.
We're going to go by color of the microphone. 'Cause
all right.
if he doesn't have a microphone, we won't be able to hear him.
Okay.
So I think the next microphone is red microphone somewhere. Yes. Red microphone.
Yes, my question is, the big picture is that with all this volcanism spewing energy into space, would not the surfaces start to collapse over, planetological time? And here on Earth, if we were to exploit geothermal energy, as some people have proposed, we've been exploiting aquifers here on Earth, and the ground has subsided. And if we were to start exploiting geothermal energy on a large scale, would not the ground subside? And so would this happen here on Earth, or also in the solar system where energy is being spewed out?
Actually, I'm not sure I got everything in your question, but geothermal energy in Iceland, they have done that for decades and decades. And the ground doesn't really subside because, what happens that they use the heat of a magma chamber or hydrothermal system that's relatively close to the surface to heat water pipes. And that's what generates the electricity. So it doesn't really cause the ground to collapse. Geothermal energy is really good where you can do it, but it doesn't mean that just because you have a volcanic area, you can actually do it. For Iceland, it's worked exceptionally well.
I think the other part of the question was, is the surface going to subside on places not Earth where there's this sort of activity?
Where there is like plume activity, for
Yes,
example.
yeah, that's right. Yeah.
Volcanic calderas do collapse, but that's mainly caused by the withdrawal of magma from underneath. So if the eruption stops and the magma withdraws, that causes a collapse of the caldera, and that's what happens on Earth, quite often, or has happened on calderas. But the plume activity, we haven't seen really evidence of a collapse. It would be interesting to look at, for example, the Prometheus volcano with high resolution to actually see, yes, if there is some collapse in the flow itself happening. But we don't have the resolution to do that.
So you think it would be small scale, not large
Yeah,
scale?
it would be small scale.
All right, thank you.
Let's go to the blue microphone, but let me remind people who have questions, please keep your hand up long enough for somebody to bring the microphone to you. Blue microphone.
My name's Heidi Hamill, and I'm a guest. I didn't hear about Neptune's moon Triton.
Oh, yes, I know. I am so sorry, Heidi. I love it too, but the lecture was just getting too long.
But it does have.
It does have. It does have possibly cryovolcanoes. It has plumes. It's very interesting. Voyager observed a couple of plume streaks and some features on the surface that we think are cryovolcanic. So I think they are cryovolcanic, but the plumes themselves, there was also an explanation about kind of like greenhouse effect, that you have this nitrogen ice layer that's very transparent, and solar radiation can heat the gases underneath and then cause the plumes. So it wouldn't be like quite, a cryovolcanism, and it's one of the reasons we need to go back to Triton, is to find that out.
Red microphone.
Hello, I'm Chris Hirschman, and I had a question about your images of Io from Juno, and I was expecting to see plumes, but I didn't see them in the pictures, and I wondered if you could explain that.
Okay. Yes,
Thank you.
actually, Juno did detect some plumes. Not many, and mostly you need like the right geometry to be able to detect a plume, because you detect them on the limb. But it did detect some plumes. I just didn't have the pictures, and it was all with the camera.
Blue microphone.
All right, John Chambers, non-member. I was wondering if active volcanism creates any sort of magnetosphere on these moons that would protect life from high energy particles, as opposed to kind of a dead Martian surface.
Not the. Do you mean volcanism of any kind? Yeah.
Well, I assume if there's volcanism going on, there's an active core.
Yeah,
and
an active
there's
core.
rotation of the core, and that would create a magnetosphere around the moon.
It depends, because for example, Io does not seem to have its own magnetic field, and Mars has a very weak magnetic field now. So it's not quite my expertise, but it probably depends on the state of the core. What Io does is it can create like a connection to Jupiter, and material from Io can impact other moons, because it gets around on a torus, and it can create actually creates a footprint like on Jupiter. But that's not quite what you're asking.
So materials accrete from the moon. to
yeah,
the planet
because the materials
via
are
magnetic
spewing
lines.
out, in space. So they end up on Europa, and they end up on, Jupiter, carried by the magnetic field.
Okay, thank you.
And, St. Casey actually can answer that question.
You have to get a microphone
Yeah,
first.
okay.
No, get a microphone.
Okay.
Behind you. There's a blue microphone behind you, Casey.
Because Casey can answer that better.
I get two microphones.
Yeah.
I was going to ask
No,
two
name and are you a member?
questions. Carrie Liss, I'm a member, vice president of PSW. So fantastic talk. I've heard two questions that actually led follow-up. One very quick. So Triton has plumes, but no imaging of volcanic structures, whereas Pluto has no plumes, but we think we've imaged volcanic structures. That's correct.
Yeah, there are no volcanic structures on Triton, but we see some very smooth areas that we think were formed by cryovolcanism.
The other question, this may relate to the question we just got. Io does not have a gravitationally bound atmosphere, but it has an atmosphere that's supported by the plumes and all the outflow. So it has like a comet, it's actually supporting steady state outflow.
The volcanoes create a local atmosphere, yes. Io has a very, very tenuous atmosphere.
If you turn the volcanoes off, does the atmosphere go away?
Good question. There could still be some sublimation, maybe. But locally, we know that the atmosphere, the density varies. So, the volcanoes kind of create more of their own atmosphere.
Interesting. And as you point out, we also know about the Io flux torus.
Yeah.
We know Io makes its own ring around Jupiter,
Yes.
which then dumps on Jupiter's poles.
Yeah.
And that's what you're getting. So there's a net current and material, and that's what was being asked before. Does Io then have this, like our ionosphere, which gets supported by material coming in as well as material coming from the Earth? Does it have a very interesting upper atmospheric structure?
Yeah. Well, it does. It's again, not my expertise.
Not mine either. This whole torus and this whole region around Io that Io's volcanoes create, it's very interesting because it impacts the Jupiter system. It's called the Ioplasma torus, if people want to look it up.
Yeah.
So would Yuck Young be somebody to talk to about, possibly about the atmosphere of Io, or is he more like Pluto?
Yuck, what?
Yuck Young? I don't know if you know.
Oh, yeah, I know Yuck very well. I work with him on Titan.
Okay.
But he's been working more on Titan now.
Okay.
Yes. Well, I should ask him. Yeah.
Let's
Thank
go
you.
to the blue microphone, please, wherever you are. There we go.
Yeah, I'm not a member, and I'm Shashwati. So it was a very interesting talk. So I just want to ask you one question, that this volcanism in different, so in the solar system, is it affected by the atmosphere? For example, Earth has atmosphere, and some other planets, they don't have atmosphere, or in case of Venus, it's a very different atmosphere they have. So now, is it affected by, the volcanism, the type of volcanism, is it affected by the atmosphere?
It's kind of a complicated answer, but for example, Io has these plumes, and if Io had a dense atmosphere, the plumes wouldn't go so high. The plumes on Io can go actually 500 kilometers high because they are essentially erupting in a vacuum. So, a whoosh out. While a Venus has a dense atmosphere, and detecting a plume on Venus would be, much more difficult. In terms of detecting it with, optically you couldn't really do it, but you'd have to detect it from the gases coming out of the plume, and the not just the atmosphere, but the environment. For example, if a planet has an atmosphere, the cooling of a flow will be faster because of more convection. So there are things that, factors that an atmosphere certainly impacts.
Thank you.
I think that will be the last question. So let's thank our speaker.
Thank you. Collect this later. All right.
And before we let her go to the social hour, we do have a few gifts that we'll be giving her. One is a framed copy of the announcement of her talk, signed by all the members of the General Committee on behalf of all the membership. A ribbon of PSW with 3 stripes on its side, symbolizing the Henry, the unit of inductance named for our founder, Joseph Henry. And a copy of volume 17, first edition of the PSW Science Bulletin, originally founded as the Bulletin of the Philosophical Society of Washington. This bulletin is a compendium and brings together 3 histories of PSW, the founding documents, the original address of Joseph Henry, and the President's lecture, in which he discusses why it was called the Philosophical Society, which in those days meant science, why the organization was formed, and some still useful comments on how scientific discourse should be conducted. And I commend to all of you to read it, because it's very relevant today.
Yes.
And with that, I thank you very much.
Yes. Thank you so much. It's been a pleasure.
Just take it off.
Okay.
Before we go, we have some closing remarks, mostly to let you know the upcoming lectures. And our next lecture will be the 2527th meeting of the Society on December 19th. And the speaker will be Davey Smith of the University of California, San Diego. He has spoken here once before during COVID, gave a very interesting lecture. I suggest that you might all like to go back and listen to it. Anyway, this time what he's going to talk about is rapid autopsies. That is, autopsies conducted very soon after a patient expires. And the point is that decomposition and the changes in the physiology and the disposition of viruses in the body is very quick. And so if you do your autopsies a day later, you will not find where a virus is hiding. And so he has undertaken a program to be able to conduct autopsies very quickly after a person dies, particularly interested in finding out where HIV hides in the body. I think you'll find that very interesting discussion from many different viewpoints. So I hope you'll all come and hear Davey. Going into that would be the last talk of the year, by the way. So you can come here and celebrate the end of the semester as well. Then beginning next year, we have a talk by Bernard Carlson, who is a biographer of Nikola Tesla. And guess what? He'll be talking about the scientist Nikola Tesla, the inventor Nikola Tesla, and not the car. The annual President's Lecture will be on Jan 23rd, 2027. 2026. I'm getting ahead of myself here. And the speaker will be Gordon Guyatt of McMaster University, and I'll be speaking about a system that he's developed for evaluating and grading the reliability and cogency of evidence relating to clinical care. And the rest of the semester is listed here. We'll be announcing the other speakers in due course. Please check the PSW Science website often to get up-to-date information, not only on who's speaking, but also we periodically update their bios and the abstracts of their talks. The website, of course, is www.pswscience.org. Let's thank the people who ran the cameras and our director in the back of the room. Let me remind everybody, return your badges before you leave. they cost money, and we'd rather spend the money on other things. So there's a big sign in the back. Just please take them off and leave them before you go. And with that, I will entertain a motion by a member to adjourn the meeting. Yes, Bob is always reliably the first to motion. Second, all members in favor of adjournment. Anyone opposed? The meeting is adjourned.